Hello everyone, my name is Stan van Wingerden. It still says the previous, oh yeah, that's right, cool. My name is Stan van Wingerden. Like my colleague Jesse Hoogland before, I work for TAIS, where I am responsible for planning, finances, and maintaining some of our internal tools, but that's not what I'm going to be talking about today. Today I'll be talking about what promise singular learning theory has for AI alignment. And I want to start briefly with a recap of the last hour or so of talks by Professor Ayagi and by my colleague Jesse Hoogland. Jesse gave us a brief overview of SLT, a primer of the most important results from it, and also motivated the case for why we should care about singular learning theory or learning theory more generally. Then Professor Ayagi gave us an example of how the singular learning theory, well, sausage gets made, as it were. She presented a result that was very important to one of the key questions that TAIS was struggling with. But we'll get to that in a bit. Most of the last hour has been about theory. This will be about impacts to alignment. And I'm structuring this using this diagram of Jesse's, the correspondence between geometry, structure, and development as suggested by singular learning theory. And I'm going to be answering what this means for alignment, and we'll see that all three of these different things have separate contributions that they can make to alignment. In this talk, I will be going over a bunch of references. Some of these Jesse discussed before, but I'm going to place them in a different context. I'll be discussing different takeaways from them. I also want to emphasize that whenever I say we in this talk, I don't just mean TAIS, I mean a very diverse group of people. We're working with a bunch of different collaborators, and none of the things that I'm going to be talking about here could have existed without the work of all of these people, and we're very thankful to them. Right, so let's get into it. So the way I'm structuring this is first I'm going to briefly discover the past of singular learning theory for alignment, some of the key issues we struggled with in the past, moving on to our present thinking on the matter, and then finally ending with some more speculative future notes. So in the past, now if you were hoping for a history of singular learning theory, you're looking at the wrong guy, but I briefly want to talk about a very short version of the history, which is the publication of the book Algebraic Geometry and Statistical Learning Theory by Professor Watanabe. Was published about 15 years ago. Now for machine learning standards, maybe that's extremely old. For mathematics, I wouldn't say that's quite true. Recapping the things that are in this, Jesse already mentioned this previously, but regular statistics is not the right tool for analyzing singular models like neural networks are. Instead, we should use SLT, and SLT suggests some more refined notions of things to measure rather than generalization error being proportional to things like model size or parameter count. Instead, we should use more sophisticated measures like the local learning coefficient. Skipping over a lot of work done before this and a lot of work after this and moving ahead to about 1 year ago, a small group of us first started to think about what this could mean for alignment. And the first formalization as an answer to the question that we ended up with is developmental interpretability. The idea that using singular learning theory, we can make a foundation for understanding learned structure in neural networks. This was our first attempt to answer this question, and the idea was that this developmental perspective would reflect geometrical things in the model, which would then in turn reflect algorithmic structure the model learns over the course of development. The idea was to kickstart a theory experiment feedback loop, as it were, by starting at a place that we can do quick experiments. So we then narrowed this down a bit more, and about 8 months ago, we formalized a couple of more questions. Can we actually estimate this local learning coefficient that SLT talks about? Second of all, does this idea that this developmental approach helps understand models, does that even make sense, or does all structure show up at the same time? Third of all, using this theory or using this perspective, can we make non-trivial predictions about simple models? I think the answers to these questions were all positive, so let me walk you through the key results. In the quantifying degeneracy paper, we found that the local learning coefficient can actually be estimated. On the right-hand side, we see that it gets the values correct in some very simple normal crossings from SLT. And on the left-hand side, we see that the ordinality in 2 million parameter MNIST models is preserved. Now this is important because we probably care a bit more about relative comparisons between models in a given class than about accuracy, about models individually. So we thought this was good news. Moving on to the toy models of superposition, which is a model of superposition where we have a c-dimensional space projected onto an r-dimensional space, projected back into a c-dimensional space. Now, obviously, there's going to be some loss there, except for the fact that this model uses a ReLU. So the right way or the best way to make this reconstruction happen is by projecting this c-dimensional space in superposition into the r-dimensional space. I won't get into too much of the details here, but what we found that yes, there's actually phase transitions. These phase transitions co-occur with increases in the local learning coefficient, and specifically I want to draw your attention to the middle two plots. On the left-hand side, we see that using estimated local learning coefficients, what phases are predicted by SLT. On the right-hand side, we see empirically what phases are actually favored in the posterior as approximated by MCMC sampling, and we see that the crossover point from the 5-gon to the 6-gon happens at almost exactly the dataset size that SLT predicts it should, using, again, these estimated learning coefficients. So that's good news. That's in this toy model, non-trivial prediction that SLT or this developmental perspective makes. So far so good. We thought LLC can be estimated. This seems sensible. There's some non-trivial predictions to make, but let's move the goalposts a little bit and let's try and see if this is actually scalable, if this gives us traction in understanding larger model behavior in non-toy settings, and if this can have something to say about alignment. Which brings us to the present. So recently we put a bunch of papers on the archive. The first of these is about scaling the local learning coefficient to about 100 million parameters. Furman and Lau devised an algorithm for calibrating the local learning coefficient estimates, which we see in these deep linear models from Ayagi's talk before, gets the estimates to the right order of magnitude, even though there's still some noise here. It also satisfies some other desiderata, which I won't get into here. But I want to emphasize that this was a big deal for us. We didn't really know whether this would scale. We only had ordinality in relatively small models thus far. And Ayagi's formula on the exact quantity for local learning coefficients in deep linear networks made this possible. So we're very grateful for this contribution. We also looked at in-context learning. The reason we cared about in-context learning is that this is a safety relevant thing. What happens in context learning is that models get better at making predictions as their context length or as they see more inputs. This starts being safety relevant because it's in some sense when models start to learn from data, not through weights, but at runtime. And we found here that although phase transitions aren't really visible when looking at the loss, we see that we can actually divide the developmental the developmental progress into several stages. So this is not, we kind of loosened the definition of phase transitions and rather talked about developmental stages. This local learning coefficient increases within a stage, flattens out at stage boundaries, increases again, flattens out again. We saw this across two different kinds of models, 3 million two-layer attention-only transformers and 50K linear regression transformers, giving us some confidence that this is a more universal phenomenon. There should be a little hat here, sorry about that. Furthermore, these stages are interpretable. In the language model case, we found, using standard MEC-interp techniques, that the model first learns bigrams, two-place statistics of language, then n-grams, essentially n-place statistics of language, before forming first previous token heads and then induction heads. In the linear regression transformer, we saw something very similar. We also used another technique, which we call essential dynamics. In essential dynamics, we take a subsample of our data set, pass it through the model for every one of our checkpoints. We then get a giant matrix of, size of the subsample times number of checkpoints times, number of tokens or logits, which is a humongous tensor that we can then apply principal component analysis to. This is similar to what Anthropic did in the toy models of superposition paper. Not sure if that's the right one, but you can look up the actual reference. What we saw is that there's curves in this PC space co-occurring with boundaries between stages. This happens not just in the first two principal components, but in the third as well. These three PCs explain about 70% of variance in this original matrix, so it's natural to ask, What's in the middle here? What's the thing that the model is sort of curving around? These points we call forms, and because they live in PC space, we can lift these forms back up into the original high-dimensional logit space. We've printed the top 15 logits here, and we think that this form is itself interpretable. This form seems to be doing something related to word completion, which is where the next word starts with a space. If you look closely at this graph, there's a second point where this happens. Give you a second to see if you can see where it is. The answer is here. We think this form is associated with induction. Now, for the sake of time, I won't get into the details here. The takeaway from this paper is that yes, although phase transitions don't show up as discretely, developmental stages do exist, and we can interpret them for large models using the LLC, mech-interp techniques, and essential dynamics. So the answers to the question of whether it's scalable and tractable are yes. The answer to whether it's relevant, I think, is also yes. But if we want to solve alignment, there's much more we could do. And we also need to do it a lot faster. So that brings us to the future. Now, I want to clarify here that this is future work. Therefore, it's more speculative, and it's on a different evidential basis than the previous. So please keep this in mind. There's two kinds of future work I'm going to talk about. The first of these are projects, which is, say, things we're currently doing. The other is things we're going to do in the future, even more uncertain. First off, we're doing dev-interp on even larger models. We're doing dev-interp right now on GPT-2 small. What you see here is the first output of that using a little dashboard. So that's how you know that's an in-progress work. And we're developing weight and data-restricted variants of this essential dynamics and of this local learning coefficient to help review new capabilities of models, possibly in an unsupervised fashion. We hope, apart from helping with interp, that this would help with a new type of evals, possibly building towards understanding-based evals. We're also doing dev-interp of reinforcement learning models in a very similar way. The hope here is that we can find, through these essential dynamics techniques, something like goal formation or self-identification. Apart, again, from having impact on interp, this could possibly also help clarify thinking about treacherous turns or sharp left turns, where our reinforcement learning agents suddenly do something different. Now, taking a step back, recall that dev-interp was just one formalization of what singular learning theory could contribute to alignment. The actual picture Jesse introduced looked like this. So it's natural to ask, apart from this developmental perspective, what could geometry and structure contribute? Now, this is where we get into even more speculative territory, but I want to briefly talk about what these two things could do. So for geometry, we call the project structural generalization. Because the model, architecture, the data set, and the geometry all interact, it's natural to ask what effect a change in the data has on model geometry. This could help answer questions of where structure could break, where it breaks, and which parts of the data could be responsible for it. A similar and maybe easier question is, what's the effect of fine-tuning on model geometry? Can this shed light on what sort of stuff gets destroyed during fine-tuning, for example? Now again, apart from impacts on interp, this could namely help with mechanistic anomaly detection, or more generally provide a theory of out-of-distribution generalization. Moving on to structure, we can try to cast the problem of program synthesis as a project of statistical inference. So in program synthesis, a program gets constructed from lower level algorithmic specifics. Similarly, in statistical inference, the data informs an equivalence class of parameters. And the way that we can make these two talk to one another is by, for example, giving certain smooth relaxations of Turing machines. These smooth relaxations of Turing machines are essentially statistical, which brings the toolkit of SLT into play when talking about programs and proofs. We hope that this idea or this approach could help formalize thoughts about inductive biases. As mentioned before, Daniel Murphy has a post out clarifying that in this smooth Turing machine setting, the local learning coefficient includes error correction. So it's possible for these smooth Turing machines with error correction to have a local learning coefficient than those without. This could also help with foundations of interpretability, as it could allow us to help look for what, for example, a for loop could look like geometrically. So the answer to the question of what could SLG contribute to alignment is threefold. From the developmental perspective, we can hope to understand internal model structure using what is known as developmental interpretability. And we think this is looking pretty good thus far. We have some experimental evidence, even though there's a lot more to do. Somewhat more speculatively, the two other things we set out to do are understanding out-of-distribution generalization through this correspondence of geometry, model architecture, and data. We call this structural generalization. Thirdly, we hope to shed some light on inductive biases through this project of the geometry of program synthesis. Which brings me to the end of my talk. If there's more that you want to know about this, I suggest you follow these links, join the Discord, look at the list of publications, or just play around with the tools that we've built for estimating the local learning coefficient yourself. Because if there's one thing to take away from this, when it comes to relating SLT to alignment, there's simply so much more that we can do. Thank you very much.
All right, I know you're all probably pretty hungry, but any questions before we clock off for lunch?
Hi. I was wondering if you could, I know it was in the future speculative section, but the SLT for anomaly detection, obviously the SLT, we're normally just talking about the weights. So is it the idea that we're sort of understanding when we're going into different functional parts of the weight space? Or could you just expand on that intuition a bit, please?
Yeah, that's a good question. So the idea is that you want to, let me formalize anomaly detection as seeing sort of which parts of the data either sort of have the unexpected behavior that we're looking for, and a sort of theory of generalization of how the data influences model geometry and thereby influences model structure could help answer that question. That's the idea behind it. Now, this is still in the sort of gestational phase, right? So for more details, you just have to wait for a little bit.
Thank you. This may be a follow-up question. I don't understand this area well enough, so I don't know. You'd made a suggestion that there was a had you suggested there was a relationship between the phase transitions and then changes in model behavior, and if so, is that where we need to be particularly concerned about assessing? So
in the toy models of superposition case, I would say yes, because the change from the foregone, the sort of projection of 4 dimensions into the 2D space, to the 5 dimensions in the 2D space, that's a phase transition. In these language model cases that we saw, this isn't as discrete. We talk about developmental stages rather than phase transitions, but still it seems like maybe we can try to use the learning coefficient to detect changes in these developmental stages. ICL suggests that this is possible, the ICL paper I should say. That's not to say that we've attempted this in a like larger setting, for example, in GPT-2 small. You probably need to do some more sophisticated things. But I think the intuition there is right that this could help with that. But I think we need to do more in order to be confident of that.
Is there a sense, sorry, I might have missed this as well, a sense in which a developmental stage is a generalization of a phase transition? Is that what you were just suggesting?
I think it's more of a loosening of the idea of phase transition. So there's not really critical points in this extremely high dimensional phase that the model passes through. So you have to let go of this somewhat, of this notion of even though the developmental process is influenced by the critical points, you don't really pass by them anymore. You spend some time in their influence. So it's a sort of loosening of this idea because it probably doesn't apply exactly to larger and larger models.
So a phase transition occurs at a particular point, a developmental
are a bit fuzzier, yeah. So in this picture that I showed before, the boundaries are relatively clear, but you should think of them as somewhat smoother, and everything happens a bit more continuously than in the toy models of superposition case, where these changes happen much more suddenly.
Okay, let's talk after. Thank you.
Sounds good.
Can we get a mic over to Espen?
So I'm curious how SLT. So SLT introduces this sort of quite crisp distinction of when how a model is developing, right? How does this compare to, for example, existing mechanistic interpretability techniques, or just at every step of learning, rerunning a series or a suite of evaluation tools? And what do you think you can garner more, or differently, or complementary to these methods?
Yeah, I think it's mostly the third. I think it's mostly complementary. If you look at standard mech-interp techniques, I think the ICL paper shows that these two things go together really well, and probably you want not just a developmental perspective. I mean, unless this whole geometry of program synthesis works out like 10 years from now, right? But so far, I think these things are complementary. They could work well together. But the success of one also doesn't really depend on the success of the other. Maybe we can see more, maybe there's developments in mech-interp.
Thank you.
Do we have a question from the live stream? We've not had one for a while. No? All right. There were some hands raised towards the back of the room.
Thanks. Yeah, not very related to alignment per se, but if I'm training a model and I look at the curves of the local learning rate, can this help me in any way train faster, or maybe control some hyperparameters and essentially use it as a developing tool rather than as a monitoring tool?
I don't know. That's not really something we're looking into, because that's not really the motivation for doing this in the first place. So, no idea.
Thank you very much for the talk. The ideas about program synthesis via singular learning theory were really exciting. And could you please tell just a little bit on what's the status? I mean, are you planning to do this, or you are actually already doing something? And if so, like, do you have...
So if you want to read more
plans?
about this, let's see if I can still control my presentation. There's a post on Less Wrong that clarifies this idea of this smooth relaxation of a Turing machine. I'm not going to walk through my entire presentation, but that's something you can read more. I think in this specific setting, we can already say things. Now, what the impact that has on alignment, that leads to a lot more work, and that's something that's a much longer research project. But if you want to know about the exact status, I suggest you read that.
Okay, thank you very much. Thank you.
Thank you, Stan. This is a very interesting talk. Excuse me. How expensive is performing this LLC estimator during training? I mean, I assume that there's some bounds that you're not on every pass. You're not running an estimator, and these graphs that you drew are not super high resolution. How expensive are these?
So roughly, I think right now, it's about as expensive as training the model. This is not something we've optimized at all. There's probably a lot that we can do here, but because we're dealing with small models, this just seems acceptable, seems fine to do. Essential dynamics is a bit easier to do because you do forward passes during training anyway, so that's maybe a little bit cheaper. But right now, if you take away from this order of magnitude the same, I'm happy.
All right, thank you very much.
Thank you. Sorry for jumping in again. I'm curious if you know of the application of computational mechanics to learning dynamics in networks, and how you see that sort of relate that perspective on learning to dev-interp in this case.
Yeah, again, I would say that these are complementary perspectives. I think computational mechanics talks about specific ways of analyzing model internals. Maybe there's a useful contribution to be made there. I don't know what that would look like, and I'm not enough of an expert in computational mechanics or SLT to judge.
All right.
We have one more question from the front.
Thank you very much. And in this slide, you talk about out of distribution generalization. So is it applicable? I'm not familiar with this single SLT, but is it possible to use this in reinforcement learning, like offline reinforcement learning?
That's a good question that I haven't thought about. I think hopefully if the structural generalization program works out, then yes, that's something you want to say something about. But as this is still sort of gestational, something we need to develop our thoughts more on, I think it's too early to say.
There is no work yet.
I mean, there's in progress work of DevInterp of reinforcement learning, but not on structural generalization.
Thank you very much.
One more, maybe? Manuel?
Thank you. So I was wondering if you could add like a few words. I was very interested like with the beginning of your presentation about in context learning. So in context learning, like in my understanding, is still like, you know, a bit of a mystery to some extent. So I'm going to ask you very boldly, do you think you solved in context learning? Do you think we now get it?
No, I don't think we've completely solved it. I
What
think
are we
it is.
missing?
Sorry?
What are we missing?
So, I mean, this is again speculative, right? But I think there's something that's interesting that's going on in context learning where we want to do interp on algorithms that the weights execute rather than the weights themselves. And that's a tough problem using standard mech-interp techniques. Now, maybe I'll be surprised and we get big progress in this direction. That I would love for that to be true. But I think maybe there you want to have a more statistical description of the algorithm that the model executes. I think, again, this is future work. Maybe SLT is a good fit for this, but this is not work we started on.
Okay, I think I'm going to draw things to a close there. So, thank you, Stan. Lovely to have you.